All right, 10.5 is the last section that we work with this counting strategies in. And there's two distinctly different types of problems. One problem is considered a not problem, where we're going to find the number of ways something is going to not happen. Okay? And the other one is an or problem. Here's the deal. Not problems are kind of messy, and or problems are really easy. Okay? We're starting with the not, because that's the order of the section. But just know that the other part of the section is the easy part, and it's coming up. All right, so not problems are going to use what's called the complements principle of counting. The complements principle of counting, we've actually seen this formula before with different context. We saw it back when we did Venn diagrams in chapter 2. Okay? It says the number of ways a certain event can occur is the total possible occurring ways minus the ways it cannot occur. And then there are 3 equations given that are really all the same equation, just solved for different pieces. The one that you will see us use most frequently is the first one. Okay, so if you flip through your examples 1 through 4, we're not doing all of them right now, we're just going to do the first one. But you'll notice that all of them have a very similar structure in the way the question's asked, besides the fact that they happen to be about cards. That's not the point. They all give you a description, and then in parentheses afterwards, they ask you to think about what is this the complement of? Do you see that? So when we're working in section 10.5 with not problems, we're looking for the complement that's easier to find than what we're asked to find. Okay? So if you take a look at the first one, for example, it says we want to find the number of ways that we get at least one card that's not a club. What does at least one card that's not a club mean? Well, it means that I could have, 4 clubs. The 5th one's just not a club. But it also means I could have 3 clubs. And it means it could have 2 clubs, and it means it could have 1 club, and it means I could have 0 clubs. And if I calculate that directly, I have to calculate the combination to get this one, and all of them. I have to calculate all of those things. It's a lot of calculating. What's the thing that can't happen and satisfy this criteria? Well, I can't have all clubs. If I had all clubs, I wouldn't have at least one that's not a club. It's a lot easier to find the number of ways to get all clubs. So this is the complement of having all clubs. So identifying something that's easier to work with and then doing a little subtraction is a much better approach than finding the number of ways of getting 4 clubs, 3 clubs, 2 clubs, 1 clubs, and 0 clubs. I'd have to calculate 5 different things. 5, that's a lot. Compared to on this option, I'm going to only have to calculate one thing. Okay? So what does this look like? Well, the the complements principle that we just identified says that the number of ways of getting, and I'm going to write it out with this description, the number of ways of getting at least, actually, let me say it differently. Instead of saying at least, just to write it shorter, I'm going to say not all. Not all clubs. That's the same thing as at least one that's not a club. not all clubs is the same as calculating the number of ways of getting anything minus the number of ways of getting all clubs. Does that make sense? That's this formula here. Notation, remember, in parentheses means number of something. That's the notation we explored back in chapter 2. Now this one happens to tell us the original value at the beginning. It tells us that there are a total of 2,598,960 5-card poker hands, which we found back in section 10.3 anyway, right? So that's the number of ways of getting anything to happen, 2,598,960. How do we get all clubs? Well, you know, we did it, but we did it for diamonds. How many clubs are there? 13. How many do I need to create if I'm creating a 5-card hand? 5. I need to select all 5 of them if I'm creating a 5-card hand. But I know how to do 13C5. I've already done it today, and so have you. If you have a Pascal's triangle big enough, you could use it on this. That'd be fine. It wouldn't be terribly much bigger than what we already had. If not, you're going to use formulas. You're going to select 5 items, and you're going to not select 8 of them. 8 and 5 is 13. Sorry, I did this before, and then I accidentally hit the wrong button. All right, so we have that same 2 million number showing up again. We're going to write down our 13 until we get to 8. So 13, 12, 11, 10, 9, and 8 factorial over 8 factorial, and then 5, 4, 3, 2, and 1. So my 8 factorials are going to cancel. What else? Yep, 4 times 3 is 12. 5 times 2 is 10. So I'm left with a 13, an 11, and a 9. What is 13 times 11 times 9? 1,287. It's the same number I got before when I did all diamonds. And if I subtract these, how many 5-card hands are going to have at least one that's not a club?
2,597,673.
The answer is most of them, right? That's pretty good odds you're going to get not all clubs, right? So when you see this phrase, at least one, another way of saying it is saying that it's not all. And the complement of not all is all. Right? We worked on quantifiers like that. Do you remember? This is one of those places where there is a little bit of overlap between the sections that we've done before. And we'll stop there for today.